A single misplaced decimal point or a misunderstood unit of measurement has deleted the equivalent of a modern national budget in a single afternoon. When we build at the edge of human capability, the margin for error shrinks to nothing. History is littered with the rusted remains of megaprojects that failed not because of a lack of ambition, but because of a single overlooked geographic or mathematical detail. We are looking at the 5 most expensive engineering catastrophes caused by simple, avoidable lapses in logic. These are stories of how a king's ego, a surveyor's mistake, and a physicist's oversight led to total destruction. The most shocking of all involves a bridge that collapsed twice because the designers were too proud to check their basic addition. Number 5. The Vasa ship. In 1628, the Swedish Empire was desperate to project power across the Baltic Sea. King Gustavus Adolphus ordered the construction of the Vasa, a warship intended to be the most heavily armed vessel in the world. It was a masterpiece of wooden engineering, adorned with hundreds of ornate sculptures and 64 heavy bronze cannons. However, the king was not a shipwright. During construction, he insisted on adding a second deck of cannons to increase firepower. To accommodate this, the builders were forced to build upward without widening the hull. The math of stability is unforgiving. A ship's center of gravity must stay below its center of buoyancy, but the Vasa was now dangerously top-heavy. Beyond the king's interference, a subtle technical disaster was happening in the shipyard. The builders were using 2 different systems of measurement. One team used the Swedish foot of 12 inches, while another used the Amsterdam foot of 11 inches. Because the blueprints were shared across teams using different rulers, the hull was built with an asymmetric profile. One side of the ship was literally heavier and wider than the other by several inches. On its maiden voyage, it sailed less than a mile. A light gust of wind tilted the hull, water rushed into the open lower gun ports, and the pride of the Swedish Navy sank in minutes. Thousands of oak trees and years of labor vanished into the mud of Stockholm Harbor. The cost was roughly 5% of Sweden's gross national product at the time. It remains a reminder that even the grandest empire can be brought down by a ruler who refuses to respect the consistency of a ruler. Number 4. The Tay Bridge disaster. In the late 19th century, Thomas Booch was the star of British railway engineering. He designed the Tay Bridge in Scotland, which was the longest bridge in the world at the time. It was a 2-mile-long iron labyrinth intended to showcase Victorian industrial might. But Bouch made a catastrophic mathematical assumption. He calculated the wind pressure the bridge could withstand based on outdated data. He assumed a maximum wind load of 10 pounds per square foot. He essentially designed a bridge for a gentle breeze in a region known for North Sea gales. To save costs, Bouch used cast iron for the massive piers. While cast iron is strong under compression, it is incredibly brittle. On the night of December 28, 1879, a massive storm battered the structure while a train was crossing. The lateral force of the wind, combined with the weight of the train, caused the brittle iron lugs to snap like glass. The entire central section of the bridge vanished into the freezing water, taking 75 lives with it. The subsequent inquiry found that the bridge was badly designed and badly constructed. The financial cost was over £350,000 in 1880 money. This is hundreds of millions today. The disaster effectively ended the use of cast iron in large-scale bridge construction. Bouch died a broken man just months later, his reputation destroyed by a failure to account for the simple, invisible pressure of moving air.
Number 3. The St. Francis Dam. In 1928, Los Angeles was booming and it needed water. William Mulholland, the self-taught genius who built the LA Aqueduct, designed the St. Francis Dam to create a massive reservoir. Mulholland was a hero of the city, but his lack of formal geological training led to a fatal geographic oversight. He built the dam on a foundation of Paleolithic landslide debris and sespe redbeds. This is a type of rock that looks solid but turns to mud when it gets wet. Mulholland ignored the phenomenon of pore pressure. As the reservoir filled, the water began to seep into the mountainside and dissolved the very ground the dam rested on. On the night of March 12th, just hours after Mulholland himself had inspected a leak and declared it safe, the entire structure disintegrated. A wall of water 140 feet high surged through the canyon, killing over 400 people and destroying thousands of acres of land. The failure was so absolute that it ended Mulholland's career and fundamentally changed how dam safety is regulated in the United States. The financial cost was over $13 million in 1928. That figure bankrupted the Water Bureau and forced a total redesign of the region's infrastructure. It is the ultimate example of why professional pride should never override geological data. If Mulholland had simply consulted a geologist instead of trusting his own intuition, the canyon would still be dry today.
Number 2. The Tacoma Narrows Bridge. By 1940, suspension bridge design was pushing toward leaner, more elegant silhouettes. The Tacoma Narrows Bridge in Washington State was a marvel of this aesthetic. However, the engineers focused entirely on the bridge's ability to handle static loads, such as the weight of the cars and the steel itself. They ignored the dynamic force of the wind. Specifically, they overlooked aeroelastic flutter. Because the bridge's side girders were solid steel plates rather than open trusses, the wind could not pass through them. Instead, it was forced over and under them, creating alternating vortices. These vortices matched the bridge's natural resonance frequency. On a relatively calm day in November 1940, the bridge began to twist and ripple like a ribbon, earning it the nickname Galloping Gertie. The concrete and steel literally tore themselves apart as the energy from the wind was trapped in the structure. The collapse was caught on film and became the most famous engineering failure in history. The cost was roughly $6.4 million, but the real price was the loss of confidence in suspension designs across the globe. We now know that every bridge is essentially a giant wing. If you do not account for the math of airflow, the atmosphere will eventually tear your work down. This event changed wind tunnel testing forever, ensuring that no modern bridge would ever dance itself to death again.
Number 1. The Quebec Bridge. At the turn of the 20th century, the Quebec Bridge was meant to be the longest cantilever bridge in the world. It was a project of immense national pride for Canada. The lead engineer was Theodore Cooper, a man of such immense reputation that he rarely visited the site. He preferred to manage the project from New York. This arrogance was the project's undoing. The team made a fundamental mathematical error. They underestimated the dead load, which is the weight of the bridge itself, by a staggering 8 million pounds. They had designed the steel members to support a weight that was significantly lighter than the actual structure being built. As construction progressed, the steel began to bend and buckle under its own mass. Local engineers noticed the deflection and telegraphed Cooper. He dismissed their concerns and believed his calculations were infallible. On August 29, 1907, the south arm of the bridge collapsed in 15 seconds, killing 75 workers. The project had to be restarted from scratch, only to suffer a second collapse in 1916 due to a faulty casting. By the time it was finished in 1919, the cost had ballooned from $7 million to over $25 million. This failure remains the deadliest engineering disaster in Canadian history. It led to the creation of the Iron Ring ceremony for Canadian engineers. New graduates are given a ring made of iron to be worn on the pinky finger of their working hand. It serves as a constant tactile reminder that their primary duty is to the public, not to their own ego. The smallest error in a notebook can lead to the greatest tragedy in the field. History shows us that the universe does not care about our reputations or our timelines. It only cares about the math. When we ignore a decimal point or a soil sample, we are inviting a catastrophe. These 5 failures taught the world that engineering is as much about humility as it is about innovation. To see more deep dives into the mistakes that shaped our world, follow New Facto.